Okay, so I'll start by a little bit about myself. I'm Jasper. I've been using Haskell for a while. I use Haskell at work as well as doing some open source stuff. And lately, I've been trying to do some more community stuff, like organizing a hackathon and doing the summer of Haskell. And you can find me on Twitter, and I have a blog as well, which has like a blog post about this talk I'm going to give today. So if anything is unclear, you can sort of look at that as a reference later on. So this is a talk about dependent types. For some reason, it was listed as a beginner's talk, which wasn't really my purpose, but I saw that it wasn't changed. So when I was preparing this talk, I tried to make it a beginner's talk as much as possible and try to keep it as accessible as possible. And I hope that worked out. We'll see. We're going to use GHCI a lot in this talk, so I'm going to do some live coding and show some examples. It's usually not a great idea to do live coding, but in this case, I'm using dependent types, so I know all my code will work because it's been proven. So that's not an issue for this talk. And so I've done this talk in literate Haskell. So all the code is there. There's no libraries or anything that I will use. So there's no magic going on, no unsafe course anywhere. There's some, I think there's a bit too much code, so we won't be able to go through everything. But I'll sort of do the highlights and the important parts to understand what's going on and to hopefully inspire you to look at dependent Haskell yourself. And yes, like if there's a question at any point or something is unclear, just raise your hand and we can talk through it. So as I said, this talk is in literate Haskell. So I'm also going to load my slides into GHCI. And I'm going to use wall to sort of show there's no weird stuff going on, no unmatched patterns, and those kind of things. And OK, there's the first. I'm already happy it compiles. Let's switch back to my slides. And this talk actually originated from a very practical origin, which isn't always the case if you're talking about dependent typing. And it started out as this Lambda calculus interpreter I was working at for work. And it was like suspiciously fast, like much faster than I thought it should be. So I was sure something fishy was going on, right? Maybe I wasn't evaluating the right things or I wasn't using all the arguments. And so in trying to convince myself that this was correct, I used like a dependency typed list to sort of ensure that I'm always passing the right amount of arguments to every function and so on. But using a list for accessing arguments is kind of slow if you have a lot of arguments. So then I started looking into, can I use some other sort of data structure that has faster random access than a list for my Lambda calculus interpreter? Lots more stuff happened. It turned out to be fast for like some really weird, unrelated reason. But I ended up with this dependently typed heap, which I thought was kind of cool. So I extracted it from whatever I was doing, and that's what this talk is about this heap as a cool example of dependent Haskell. OK, so before we go into the what, I'll talk a little bit about the why. Like, why would you ever want to use dependent types? Fortunately, this is a Haskell conference, so I don't think I will have a lot of trouble convincing people that dependent types are useful, because it's just like a step, taking Haskell and just going a step further, right? So if you're asking the question, does a particular programming language have types? You can ask that about any sort of programming languages. And you can sort of imagine people saying, yeah, I was using Bash before, but I moved all my scripts to Python because it has types, right? Bash only has strings, whereas Python has, like, you can create objects, you can create integers, and so on. So this is definitely a valid statement. But then you'll also hear people say, I moved from Python to Java because it has types. And Java definitely has, like, stronger types than Python. And you can make some sort of guarantees about what the input and output of functions will be. But then you'll hear other people say, yeah, I'm not using Java anymore. I used to Haskell because I wanted to have types. Because in Haskell, I can really express what my function is going to do using the type system, and I can make some guarantees about side effects and so on. So then I think going to moving, for example, from Haskell to Agda is just one step up from that. Sometimes you're working on some Haskell code base, and there are some really gnarly bugs, and you want to avoid running into them again. And so you're sort of wondering, can I guarantee that in Haskell's type system? And you can't really, and in Agda you would be able to. So yeah, that's why you would want dependent types. And of course, the advantage of using dependent types in Haskell is, so while I think Haskell is a really good trade-off in sort of the things that the type system gives you, the things that it allows, Agda is just one step further, and it's not really practical anymore for most things. But with dependent Haskell, you can write most of your code in Haskell, and then just use dependent types basically where you need them. And I think that's a very, very powerful idea. And so to conclude, having types, it's not really like a yes or no question, but like all of these programming languages sort of take various spaces in the design space, and I'm not really trying to diss other programming languages because I love all programming languages. And so, yeah, having dependent types in Haskell is just one step further up from having Haskell. And as I said, this talk is literate Haskell, so we'll skip through a whole bunch of imports that we need. Nothing too weird going on. We'll use a few libraries, but they're really standard stuff. And then we'll get into it. So we start off, as we usually do in dependent Haskell, by defining really simple piano numbers. We can either have 0 or we can have the successor of a number. Then in the second code block, we use the data kinds extension to lift this first data type to the type level. So 0 becomes a type, and successor also becomes a type. And that way, we can define numbers, types for numbers. So 0 is a type, 1 is a type, and so on. One particular case where this is useful, and this is pretty much the hello world of dependent types, is creating a list where the number of elements that's in the list is also encoded in the type. So I'm calling that vec here. I have a 0 vector, and then I can add something to a vector. And then the length, we get the successor of the length when we add something to a vector. And I'll quickly show that off in JCI. So we have an empty vector, and then, for example, we can add hello. To this vector, and then we'll have a 2-length list, and we can also see in the type that there's 2 elements because we have the successor of 0, which is 2. Why is this useful? So here's the show instance I just used. We can convert this to a normal list by just going over it. Why is this useful? Well, we can write a function like this. Head in prelude is unsafe because it can throw an error. But using this type, we can write a safe head because we can only pass in a vector that has at least 1 element. So if I try to do, for example, vec head of vno, I will get a type error, and my code will refuse to compile. So that's pretty useful. And so in this talk, I'm going to expose a similar way to deal with binomial heaps. So a binomial heap is something you can use to implement a priority queue. It basically means you can add an element to the heap, and then you can pop something from the heap. And the interesting thing is that the thing you pop is always the smallest element. And there is this correspondence in between binomial heaps that has n elements and the binary representation of the number n, which is particularly cool. And then that means we will be using binary numbers on the type level to sort of index into this type and make guarantees about its size. And I'll start by having a really quick demo. So for example, we can have the empty heap, which just has the type bEnd, which is the end of a binary number. And then we can, for example, push some things onto this heap. I'm going to push 5 things on it, D and E, to the empty heap. And then we get a heap. And the important thing is here, we get a heap with 5 elements because 101 is the binary representation of the number 5. So let's continue. And I'll take a step back first, and I'll talk a little bit about how to use dependent types in Haskell and how we can make these proofs and talk about it. So I think there's generally two ways of doing these kind of things. One is doing things by construction, which is what we did with the vector before. Because of the types we gave to the vector in the GADT, everything sort of works out by construction. V null has the type null, cons adds one to the length of the list. And the second way is, rather than sort of making sure things are correct by construction, we'll look at the results of the types and then actually have a proof about it and sort of prove that two things are equal rather than ensuring two things are equal by construction. And my general takeaway or like experience report from this doing this sort of thing is you really want to shove as much as you can into the first style of doing things, because the second is significantly harder. And so in order to provide a proof, I'm using the singletons approach by Richard Eisenberg and Stephanie Weyrich, which I think Stephanie is also here, and she's also going to give a talk today, so I'm really looking forward to that. And the gist of it is that sort of doing this dependent types programming in Haskell, it's all about equality. If I have a simple proxy type, which has a phantom type parameter, GAC doesn't allow me to write this code, sort of moving proxy A to proxy B, because X has proxy A, so it can't be proxy B, right? Even though I know that the implementation is the same. There's only one constructor called proxy. So if I try to do something like X to X, and I give it the type proxy A to proxy A, this works. I obviously can't show it, but if I try to tell it, oh, X to X goes from proxy A to proxy B, I will obviously get a type error. And in order to avoid this, I have to sort of provide evidence that these two things are equal. And this uses one very important data type called the equality proof. This is available in some Haskell library, but I'm generally defining things myself here because it's easier to go through them that way. And equality proof basically takes two parameters, A and B, and then it has a constructor sort of showing that these two things are equal, because really they are both A. So whenever I can sort of create a value of this constructor QAD, it means that I've already proven that A and B are equal. And then also, I'm using this squirrely tilde thing to make things a bit more readable. So an example of using this equality proof constructor is here, and for example, in cost, where I am allowed to write proxy A to proxy B as ID. I can't, so X is my proxy A. If I would use it right here in the code, I wouldn't be able to sort of cast it to proxy B automatically. But if we have the proof, which I've defined above, as soon as we pattern match on this constructor, JC knows that A is equal to A, so hence equal to B. So inside this pattern match right here, I can sort of safely assume equality, and GAC believes me. So that's basically all you need to do is create this equality proof, right? So let's give one short example. We have our natural numbers. We add a type family to add two numbers together. If we are adding something to 0, we get something back. If we add something to a successor, we recursively call addition. And now, if I wanted to provide, or I wanted to cast something that adds 0 and n together, and I want to cast it just to n, GAC allows you to do that by default. Just because you can just look at this statement here. You can just apply this case right here, and it's sort of trivial, right? So for this kind of cast, you don't really need anything. There's no proof needed. So yeah, the above one is very easy. But what happens if we try to do it the other way around? So we're switching n and 0 and trying to use ID on that as well. And that doesn't work out. GAC will give us a type error saying I can't unify this piece with this piece here. So how do we solve that? Well, as I said before, we need to be able to construct this equality proof thing. it's a value level thing. So the question is really like, how do I come up with this proof, right? I can't sort of summon it out of thin air because that's sort of the problem I was trying to solve. I was trying to say that these two things are equal. It didn't work in this function, so it wouldn't work here. So I'm obviously going to require something else. I would really like to just be able to pass in n. And then I can sort of look at n and sort of, if n is 0, well, my proof is trivial, and so on. But you can't really put the type n in there because, well, n is a type, and I need a value there. And you can't case analyze a type. And I think that's the whole gist of this singletons paper. It basically means that for every sort of, for every type, and remember that net is a type right here, because we're using data kinds. So for every sort of this type you're going to want to write proofs about, you're also going to provide this singleton. And this is very easy and mechanical to write. There's libraries which automate that. I've done it by hand here. But basically, we have a singleton mapping to the 0 constructor, and we have one mapping to the successor constructor. And the name singletons, I think, is inspired basically because for every sort of type, every net type you have, there's exactly one singleton right here and the other way around. So we can use that we can pass that into our lemma, and then we can really case analyze and do all sorts of things with n, because it's now we've sort of turned it into a value, right? And proving the base case is very easy. Adding something to 0 is going to give me 0 back. We can just put the QED here, and JSC can automatically check that this is correct. If we need to do the successor, what we do is we recursively call our lemma for n, because we can now sort of access this type value. And if this proofs obviously works out because there's only one constructor. And then inside this case, I've already proven that the other two things are equal. And then we can just apply our type family, and GC accepts this proof. So if you just look at it, it's very short and sort of intuitive to understand. And usually the hard part of doing this is sort of trying to come up with what things you need to prove and why, rather than how you prove them. At least that's been my experience. And once we have this lemma, we can do our cast. So we take this natural, we sort of provide it as evidence to the lemma, and then we can just write ID here. And that means we can safely convert in between those two things. OK. Yes.
So what about the computational cost?
There is a computational cost. And in this talk, I just sort of assume there's a big computational cost associated to it. But there are also ways, like once you've proven this, you can try to erase the computational cost. Because once it compiles, you sort of know that this proof isn't really necessary anymore, right? But for example, in this talk, I think the complexity of my operations on my binomial heap is actually not the optimal one, because I have to evaluate all these proofs everywhere. But yeah, there are ways to erase that cost. OK, so let's dig into binomial heaps. Binomial heaps are built out of binomial trees. Binomial trees are very easily defined. So a binomial heap here either is like a singleton node. There's no way to have an empty tree. Or if it's one of order k. And so it's very important to know that k is not the number of elements, it's the order. A tree of order k has 2 to the kth elements. And basically, it has this root node, and then it has all the different subtrees below. This is the Haskell definition. So a tree always has of order k, always has a root. That's the A right there. And then it has some children. And children are defined as either you have 0 children, or you have like some children. You take a tree, and then you take the next part of children, and we can see that this increases the order. It's much clearer with a picture. So these are the binomial heaps of 0, and then in 1 we have the root, and we add the tree of 0. the tree of order 2, we have a root, and then we have the binomial heap trees of size 0 and order 1, and so on. So it's recursively defined, and it's a relatively simple structure. How do we construct these? Well, we can either make a singleton tree, which is very easy, or as I sort of shown in the picture, we can add one to it. And this is important to know that if we take two trees of the same order, we put them together, and we get a new tree back, which has like an order of one more. And then in there, we sort of take care. Well, the merge is actually very simple. We just add one of the trees to the other one, but we take care to keep the least element at the root. So this is a picture of doing that. If we want to merge these two trees together, and that works out because they're the same order, B is bigger than A, so we put B as the child of A. Let's show this in GACI. Clear my screen. So I have a singleton tree with just A. I can merge this tree with a singleton tree that just has B, and then I get a tree of order 1. What doesn't work out is trying to merge this further with another singleton tree, because, as I said, you can only merge two trees of the same order. And right now, I have one of order 2, and then a third tree of order 1, and these can't be merged. So dependent types is already buying me something. Yeah, so this is where we have to introduce binary numbers. Because, as I said before, these trees can only hold collections of exactly 2 to the kth elements, so either 1, 2, 4, 8, and so on, which is not super useful for general purpose containers, of course. You want to be able to hold any number of elements. And the way binomial heaps solve this is actually very easy. So you just have a collection of these kind of trees, and for every size, you have either one tree of it, or you don't have any. So for example, if we're looking at building a collection with 5 elements, there's only really one way to do that, because we can only have one tree of each order. And so that's by having one tree with 1 element in it, and then having no tree with 2 elements in it, and having one tree with 4 elements in it. So we have one of order 0 and one of order 2. And this is where the correspondence with binary numbers originates, because the binary notation of 5 is also 101. It's basically 1 plus 4. And here we have a tree with 1 element, and we'll have a tree with 4 elements. This will become a bit more clear as we go on. But this is how we can define binary numbers. It's very simple to the net I showed before. Either a 0 or a 1, you can add stuff, and then there's an AND marker. For example, we can define 6 like this, 0, 1, 1. So one important thing to note is that we're reading binary numbers from the right to the left in this talk. Why is that the case? Well, it's a long story, but basically trying to do it from right to left is much easier than trying to do it from left to right. And one example of that already is just incrementing a binary number. I have that code right here, and it's just a single type class. Type family. If I have time, I'll show how you can increment binary numbers from left to right, and it's much more complicated. So if we increment the empty binary number, we get 1. If it's a 0, it becomes a 1, and otherwise, if there's already a 1 in place, we sort of need to do a carry. We turn it into a 0, and we carry the addition. So this allows us to define a bunch of binary numbers, 0, 1, 2, 3, by just incrementing the previous one. I can show that off as well. So kind is a thing the operator we use in GCI to evaluate this. So I have the number 3 right here, and then I can increment that by 1. Oh, I messed that up. So here we go. Then we get 4 out from left to right. So let's continue. So once we have increment, it's fairly easy to define addition. It's just a bunch more cases. If we add something to the empty thing, we just get the other thing. If we add 2 zeros, we're just going to call recursively. if there's a 0 and a 1, we can put the 1 and continue with addition. And then if we add two 1s together, we put a 0 there, and we need to carry our addition. It's basically just like how you were making sums in primary school or in high school, right? But on the type level. So that's pretty cool. And we can show that off as well. So if we add 2 and 2, we get 4. If we get 4 and 1, we get 5. So let's clear the screen here. And for example, if we add 4 and 5 on the type level, oh, I need to add them, of course. Then we get the binary number 9 down there, which is a type. Again, we have to provide the singleton. It's just a mechanical thing. For 0, there's a constructor. For 1, there's a constructor. And there's, again, like a one-to-one mapping, very mechanical. We'll use this singleton later on. So now that we've defined binary numbers on the type level, let's go back to heaps and actually use these binary numbers. And this is the definition of sort of the internal structure we use to represent the binary heap. We use a recursive approach. So a number of trees is what we call a forest. So we can either have the end of the forest, then we can add a tree to the forest, which is represented by 1, or we can choose to not add a tree to the forest, which is represented by 0. So if I have 0, there's nothing here. Otherwise, there's a tree here. And I represent that in sort of the return type as well. Like I indicate whether or not I have a tree at a particular position. And then there's sort of the tail of the forest. So there's the k as well. And sort of very informally speaking, k is the first tree I have. And then the binary number determines the shape. So if I would have something, so k is a natural number. So if I would have something with the type forest and then 3 for k and 101 for the binary type, that would basically mean that I have a tree of order 3 because I start with 3. Then the next one, order 4, I wouldn't have a binomial tree. And then for 1, so which is the order 5, I would have a binomial tree. Yeah. The binary number is still reversed, but there is something interesting going on here. So in the children I showed before, I was ordering the trees sort of from the largest one up to the smallest one. And what I'm doing here is I'm starting with the smallest one, I'm going to the largest one. And that's also the way we read binary numbers. If we do it from left to right, it's like the smallest bit goes on the left in our case. So it does work out. So yeah, and sort of the fact that we had our children in like one order and then we have them in another order here, it makes things easier now, but it's going to cause us a lot of grief later on, and we'll get to that as well.
So it looks like you're tracking the smallest tree with k as this size. So why not take a representation where if there's nothing start at 0 and get rid of that k parameter?
So we need this k because we need to be able to write recursive functions on it. And we'll have a wrapper around this, which puts 0 there. But for example, if I want to sort of look at a heap, take off the first element and do something recursively, I need to be able to call the second part something, right? So that's why we need this thing. And we'll see how that works on. So we can have an empty forest, which is pretty trivially defined. And we can insert a tree into the empty forest. And interestingly enough, we can only insert a tree of the order k, and this increments the binary number. And how that works is more intuitive to see in GCI, actually. So we can have the empty forest. There's nothing there, but we have the end of the forest, and then we can insert a tree of the order of the 0 order. So I'm just going to use a singleton tree here. And we get a 1. Oh, let me put that up to the... So we can insert like a singleton tree, and then we get a forest right here, which is one element. If we try to add another singleton tree, then there are basically two trees of order 1. So that sort of corresponds to increment, and we'll have a carry. So these two things are added together and carried. So we'll get this 0 right here. So there's no tree of order 0 anymore, and we've carried and sort of merged these trees upwards. So that's how inserting corresponds to binary increment. And the merging two forests is basically like what addition is to increment, but then for binary numbers. So if we merge two trees, I have two trees here. If we want to merge these, I can just put A in the spot where there's nothing here. That's sort of the same thing if I was adding 1 and then 0, 0, 1. I could just put the 1 there. Sometimes we have to carry. So for example, if I was adding these two things together, I would have to carry by basically merging together A and F and continue like that. So this is the definition of merging forests. So like if there's nothing in either end, I can merge them. And if there's something in this place, I have to carry, basically. And it might have been, this code looks very, very similar to binary addition. Let's give an example first, though. So I wanted to save myself some typing here. If I have 1 of order 5 and 1 of order 1. So I have this guy and this as well. And then if I want to merge these two forests, I get 1 with the 6 right there. Maybe I can move that up to the top a little bit. So by merging these two, I get a forest with size 6 in binary, and I've performed a carry there by putting the A and the F together. So why? So this is the picture again. So the question is, why is this so easy? I haven't had to provide any sort of single proof so far. Well, that's because we've sort of cleverly constructed our binary addition and our merging of trees to perfectly match up, right? In the type signatures as well as the implementation. So if we overlay this code, so you'll see that this is the implementation of merge forest. And wherever there's an end of the forest, I'll get a B end if we overlay this code. So this perfectly corresponds to binary addition. And for example, here, where I'm adding two 1s together and then incrementing, that sort of perfectly corresponds to adding two things together where there's already a tree and then inserting this merged tree. So that's why this, for now, works out so easily. Yeah, and then providing the heap is, as I said before, just a simple wrapper around this forest. And the types look very easy to read. Pushing something to a heap increments the number. Merging two heaps adds the numbers together. So far, so good. Actually, I'm going to skip this. But this is where things get a bit harder. Having a heap which you can just push things to but not get anything back from it, it's not very, very useful either. But this is where things get very complicated. So I was working on this, the thing I have right now in a couple of hours, and then sort of actually implementing popping and the rest of this stuff took me a long time. And we're going to need 4 more lemmas and another GADT, and unfortunately we won't have time to go through everything, but I'll at least want to show some of the interesting parts. And so how popping works is we have a bunch of trees, and we're going to take the tree with the smallest root, remove it, split it. Its children will form a new heap, which we can merge with the original heap. It is much easier to see in a picture. So if we have this heap right here, and we want to pop the smallest element, we simply look at all the roots. The smallest element is always in one of the roots. So in this case, A is the smallest element. And so we're going to start by taking this binomial tree and moving it out. So we get the new heap here, and we get our tree. We can easily take the smallest element from the tree, which is A, and then the children always form like a new binomial heap, because a tree always has all the children it has. So we get a new tree heap right there. So we have our smallest element and a second heap, and then we can merge the two heaps together. So the remainder of the heap, which was just B, and then this new heap we got by taking the children of the tree. We put these together, and we have a tree with 4 elements now rather than 5. And we've extracted the smallest element. And so I'm going to focus on step 2, which is just taking one binomial tree and taking it of its children and providing a proof for that. So we start off with a 3 of order k, has 2 to the kth elements. We want to remove the root, so we end up with something with 2 to the kth minus 1 elements, and we turn this into a heap. And this becomes the new heap. There's k child trees, so the new heap will have k full trees. And so if we look at the binary notation for that, we will basically just get k ones. And that matches up with our intuition, because if you write 2 to the kth minus 1 down in binary, you will always just get k ones. And instead of doing this complicated to the power thing in a type family, we can do something much more easy. We can just have a type family to have k ones, which is much easier to define and understand. So if we have 0 ones, it's simply an empty binary number. If we have one more, we add 1 to the front, and that's how we get a number of ones. So I can show this off as well. So if we have if we want 3 ones, we get 3 ones. It's a binary number. So far, so good. So let's talk about splitting this tree. Now we were able to write down its type. If we split off a tree, we get its root, we get its children, which is n ones. The implementation uses this other function called children to forest. Children to forest also has an easy definition. It just calls this other wrapper, children to forest go. And this is really where the hard stuff happens. But we pass in some more arguments. And basically what we pass in is a 0 singleton. And then we pass in another singleton, which matches this n right here. And this is one way of constructing these singletons. Again, it has a runtime cost, but hopefully we can eliminate it. And so this is just we need some way of obtaining this number n, because we want to be able to do proofs about it, and we can just derive it from the number of children. Yeah, there's also other ways to create these singletons. And so, as I said before, the tricky bit is really that the children are in one order, and then forest they're in the other order. So we want to be able to reverse these. In Haskell, you can reverse a list quite easily by going through the list and keeping an accumulator. Every time you encounter an element, you add it to the accumulator, and then you end up with the reversed list in ACK. And what we're going to do is very similar. Just the types are a bit more complicated. But we can already reason about it here, really. If we reverse a list in Haskell, we hope to get out a list which has the same number of elements as the list we put in. And so this is true here as well. And sort of how we guarantee that the output has the same number of elements is we can sort of mentally put down this invariant that the length of ACK plus the length of the remaining list is always going to be n, which is my original number. So if we write down the type of that, it gets a little bit more complicated, but the implementation is going to be very easy. So if we're putting in the x, which is our accumulator, and n is the remaining list that we still have to consume, and then we have this invariant encoded at the very top over there, saying that if I add x and n, we're always going to have m. And then we still have 2 singletons to sort of pass around as a proof. In here, in the base case, we really just want to return our accumulator. Unfortunately, that doesn't work out. our type of the accumulator is ones of x, and we're expecting something of ones is m. And so this is like a really good example of when these proof comes in handy, because we really know that n is 0, and we know that m is the addition of n and 0. So really, we know that m is the addition of x and 0. So why can't I use the addition of x and 0 as being x? Well, it's because we have to prove that, right? And as I said before, like sometimes this follows simply from the definition of the type family, but sometimes we need to provide some evidence. Yeah, so this is the expected type. Fortunately, we provided this lemma before in the first part of this talk, where we sort of prove that we can add x and 0, and we get n back. There's a typo here. Obviously, the result has to be n. And then we can use this lemma in children to forest in order to just return the original accumulator. Very much like in the base case of the list reverse, we just return the accumulator. And if we wanted to erase like the runtime cost of these proofs, everything here could be ignored and everything here could be ignored. And it sort of really simplifies itself to reversing a normal list in Haskell. The inductive case is a bit harder, and need to go a bit faster here. And GAC in this case actually does a great job and gives us almost what we want, with the problem that there's no commutativity yet for adding successors of things. Once we prove commutativity, which is lemma 2, we can write the inductive case reasonably easy as well. We call children to first to go recursively. We modify our singletons so that every call receives the right singletons. And we add this tree right here with the F1 constructor. This is our commutativity proof. Again, writing these proofs is very easy. It's sort of like figuring out which proofs you need and where you need to put them is the hard part. But that's it. This gives us the ability to break apart a single tree, which is only one part, again, of sort of popping an element from the heap, right? The rest of the code is a bit more complicated. Well, this is a more realistic drawing, so we will need some more type families, like the pop count, the number of ones in a binary number, the length of a binary number, checking if things are 0. I'll fast forward through the code, so you can see it's actually not that much. Surprisingly, there's a few utilities, type families, lemmas, and so on. This lumberjack to cut down trees, some singletons, and then we can wrap up with another type family. And we arrive at the end where the implementation is not that hard. We're actually going to use our lumberjack to cut all trees in parallel. We select the minimum root and then split off this tree, and then going to merge it back together. So the important part here, I think, is that the type signature is actually very easy to read as well. If we pop something from a heap with B elements, we decrement the number in there, which is a partial type family. Partial type families are OK because Richard Eisenberg said so, as long as if you have a constraint as well. And I'm using the non-zero constraint here, so I can't decrement 0. So if I want to show that off, then I can hopefully browse back a little. So I have this tree here. Let me clear up my screen. With 5 elements. It has 101 as its size. And then I can use pop heap on it, which is the last thing you use in GHCI. So you get a character back, the smallest element. And as you can see, my binary number has been decremented, and the size is still correct.
Can you try to pop empty heap?
So if I try to pop the empty heap, I will get a type error because false is not true. So and the false is not true comes from the non-zero being required to be true. So that's it. I'm not sure if we have time for questions, but thanks for listening.